cover there. A surd is an irrational number. I hope we are clear about what is an irrational number because previously on indices we have covered that a rational number is a number that can be expressed as a fraction. Irrational number is a number that cannot be expressed as a fraction. Okay? So a surd is an irrational number that is written using the radical sign. The radical sign refers to also the root sign. Okay? So we are going to be looking at a lot of numbers that involves the root. For example, maybe the square root of 24. Okay? So we're dealing with that in this entire chapter. Okay? Just to lay out some properties of surds. Okay, we have these three properties. Firstly, square root A times square root B equals to square root AB. It shouldn't be anything new because we have already covered in indices, okay, that square root of A is actually A to the power of half, and then after that times B to the power of half. If I have the same power, different bases, I can write it as them together with the same power. Right? Nothing new, okay, based on our indices laws. Then in the second property over here, square root A over square root B is the same as square root the entire fraction AB. Same idea as for what we have learned in our indices. And then square root A times square root A, that's very important that it gives us A. That's because it's actually looking at A to the power of half times A to the power of half. So we will add up the two powers, and that gives us A to the power of 1, which is actually A. Okay? So these three properties are very important when we do simplification of surds. Okay? An important thing about these properties is that it only applies when the base number, your A and B's, they are positive numbers. Okay, it cannot be a negative number. Otherwise, you may end up getting a contradiction. For example, 1 equals to -1. Okay? For example, if I were to say that this kind of things hold true for A and B to be negative, so important condition is that A and B must be more than 0. If I were to define the same for your negative numbers, okay, we will end up saying that -1 could be equals to 1, which we know that is not true okay, because we know that square root of -1 times -1, -1 times -1 itself is actually 1, and root 1 is 1. Okay, but if I were to apply the property, I can say that this is equals to -1. Root of -1 times root of -1. Okay? And in other words, this is root of -1 squared, which is -1. Okay? I'm showing you a problem now, okay, that this cannot hold true. Okay, so you will end up saying that 1 equals to -1. Okay, so what I'm trying to point out over there is that these properties here, A and B must be positive. You cannot apply it for negative numbers. Okay, because negative numbers as bases in our square roots, that will be complex already. They are complex numbers, which we don't cover in our secondary school journey. Okay? So this is just a sidetrack. If we want to simplify these surds over here, Okay? It should be an easy simplification. What is root 7 square going to be? Someone? Sorry. Okay, someone chose your love. Okay, Li Xuan. What is root 7 square? 7, right? Okay, because we know that square and square root, they are in opposites of each other. Okay, so root 7 square will be 7. Okay. Right. Then now I want to make use of this square root 32 to help us understand what I mean by simplifying. Because in your view, you may find that it is already simplified. Okay. Firstly, square root 32, right? The 32 itself, do we agree that it is 16 times 2? Correct? Okay, and 16 is a square number. Okay, it's a perfect square, which is 4 times 4. So to simplify a surd, we want to simplify this factor over here into 4 square root 2. Okay? So if there are perfect squares to be found within that base itself, within that number, we need to apply the square root to it. Okay, to take it out. You understand? Okay, so 16 is a perfect square of 4, so that's why we write it as 4 square root 2. And why this happens is because based on our rule over here, okay, number 1, square root 16 times 2 will be equals to square root 16 times square root 2, and square root 16 is equals to 4. Okay, so 4 square root 2. I write something first. I have to show. Okay, so I think that Juba asked a very good question. He asked, how do we distinguish 4 square root 2 versus the 4th root of 2? Okay, so we need to be very careful in our writing. Okay, so 4th root of 2, your 4 should be small right beside the square root sign. Whereas in this case, we're talking about 4 times square root 2. Your 4 and your square root 2 must be of equal size. Okay, so if I were to exaggerate it a little, okay, it should be equal size, whereas 4th root of 2 will actually look something like that. Your 4 should actually be smaller. Okay, so we need to make sure that we write very clearly between the 4th root and 4 times square root 2. Okay? Next, we look at square root 12 times square root 3. Okay, so to simplify it, there are several ways to go about it. Firstly, you may want to consider applying the first property. Okay, to combine the two roots together first. Can do that. That will give us 12 times 3 under the root, and that is 36. Okay, and for the square root of 36, we know that 36 is a square number. Okay, and that will give us 6. Okay, lastly, part D, we have square root 100 over square root 2. You could combine them together to write square root of 100 over 2 first, which gives us the square root of 50. perfect squares. That's why knowing perfect squares very familiarly, okay, will be very important. So that will be square root 25 times 2, which is actually square root 25 times square root 2. Hence, we can have the answer for 5 square root 2. Yeah. Okay, any questions? No? Okay, yes, Alex. For the what? Okay, yes, you can. Alright, for square root 100 over square root 2, you may see square root 100 is a perfect square on its own already. You can write 10 over root 2. But, okay, I have not yet introduced how to we rationalize Surd number, so I won't approach it in that way yet. Okay, yeah, I won't approach it in this manner yet because I need to later on times square root 2 times square root 2 in order to get this. Yeah, but I won't reach that yet. Okay. Questions? Okay. Next, we look at try to simplify them. Okay, in try to, we are given an expression where we want to simplify it. Okay, it's important that we need to see that they are like terms. So in part A, we see 7 square root 5 minus 3 square root 5 plus 2 square root 5. It is as good as saying it as 7x minus 3x plus 2x because it's all the same root 5. Right? Okay, so to simplify it, it will mean 7 minus 3 plus 2. So 4 plus 2, that was 6. Okay? So we also see that based on what we are doing so far, we are keeping our answers to exact form, insert form. Okay? We are not using our calculator to get a decimal number. Okay? So this is where we are trying to learn how to keep answers in exact form itself also already. Okay? So if you were to understand part A, that we want to get like terms, okay, because we have all the root 5s appearing. In part B itself, I have root 50, root 8, root 2. That will mean that in order for me to simplify this expression, I must deal with the individual roots first by simplifying them such that perhaps I can get something in root 2. Then I can sum it all up together or do the subtraction. Okay? Will you give it a try to re-express all these surds in multiples of root 2? Okay, before we actually add them up. Okay? Can you all give it a try? Yes. I give you all 2 minutes. Okay? Simplify the individual roots. Then after that, add them or subtract them together. is actually 4 times 2. So in this case, you can get 5 root 2 minus 2 root 2 plus 7 root 2. So 5 minus 2 is 3, 3 plus 7 is 10. So 10 root 2 will be the answer. Okay? Questions? Okay, next we look at try 3. You also want to simplify. Okay, we want to simplify all of this here. Okay, our understanding of our algebraic expansion, okay, remains the same using our distributive law or the rainbow method. Okay, will help us in doing the expansion and then the simplification. Likewise, for part B, you can also use your identity, your a minus b bracket square formula to do the expansion. Okay, and then in part C, you recognize a plus b, a minus b. Then after that, you can get a square minus b square expansion. I'll just tackle part A first. So in this case, we recognize that I cannot use any of my identities. I just do the rainbow method. So 2 times 5, that gives us 10. 2 times negative 3 root 5, that will give us negative 6 root 5. Okay? So I want us to be clear that when I do the multiplication of 2 with 3 root 5, I'm just taking the 2 times 3. I do not need to multiply by the 5. Okay, because the root 5 itself is just a number. You think about it as how you even go about multiplying 2 times 3 times 4. You do not do 2 times 3 then after 2 times 4 or so on. Right? It is not going to be equals to 6 times 8. Alright? We don't do that for normal numbers. So likewise, you shouldn't be doing that, okay, in terms of 2 with 3 root 5 as well. Okay? So then after we move on, 4 root 5 multiplied by 5, that will give us 20 root 5. And then 4 root 5 minus away, times 3 root 5, that will get you 12 times 5. Okay? Because 4 root 5 times 3 root 5, 4 times 3 gives you 12. Root 5 times root 5 will give you 5. Right? Okay? So simplifying it, 10 minus away 12 times 5, that's minus 16. So we get negative 15. Minus 6 plus 20, I'll get 14 root 5. Okay? This and this are not like terms. This is a rational number. This is an irrational number. You cannot add them up together. So your simplified answer will actually be this. Yes. Why is what? Why is this negative 6? Minus 12 times 5, why? Because 4 times 3 is 12, square root 5 times square root 5 is 5. Because you need to see this as okay, writing it in this manner is the same as 4 times root 5 times 3 times root 5. Right? I can reshuffle this to write it as 4 times 3 times root 5 times root 5. Okay, so 4 times 3 is 12. Root 5 times root 5 is 5. Okay, you cannot take the root to multiply by a standalone integer. Okay, questions? Okay, if you're good, will you do part B and part C on your own for the expansion? 24. So I will get 24 root 3. Okay, you will notice that in this entire chapter, your calculator can be a little bit useless because you must know, okay, what is it that you're trying to calculate. Of course, if you cannot do 2 times 3 times 4, then press calculator lah. Okay, so but you cannot add in the square root 3 because that will surely give you a decimal number. You will not get a root number, a surd number, okay, in your calculator itself. Okay, then 4 root 3 bracket square, that refers to 4 root 3 times 4 root 3. Okay, so in other words, it is 4 times 4 times root 3 times root 3. So 4 times 4 is 16. Okay, root 3 times root 3 will be 3. Right? So I will get 16 times 3, that is 48. So 9 plus 48, that will give us 57. Okay, so our answer will be 57 minus 24 root 3. Okay? Questions? Next, we look at part C. We have root 5 plus 2 times root 5 minus 2. Okay, so I hope that we can also recognize our a plus b times a minus b rather than to do the distributive law. Okay, so in this case, it will give us a squared minus b squared. In other words, square root 5 squared minus 2 squared. For which I have 5 minus away 4, and this gives us oops 1. Questions? Okay, so if we are okay with this, conjugate surds. Okay, I'll explain in a moment what is conjugate surds. This idea of conjugate surds is very important because later on we are going to be looking at rationalizing, okay, of a surd fraction. Okay, and it relies upon how we understand some expansions. Okay, if I were to look at 3 plus root 2 times 3 minus root 2, okay, what we understand over here is that I can use my a plus b times a minus b to give us a squared minus b squared. And that would tell us that it is 3 squared minus away root 2 squared. Okay, and that will be 9 minus 4. Okay, and then I will get 5. Okay, and then if we were to try another case, for example, root 2 plus 1 and root 2 minus 1. I can also do my a squared minus b squared to get this, such that I have 2 minus away 1 and I'll get 1. Okay? Yeah. 9 minus 2, sorry. I bet. Thank you. 9 minus 2, that will be 7. Yeah. Okay? So, observing how is it that we do this expansion, we notice that we are always getting a whole number. Okay? Unlike previously, when we do our expansion for this, for example, we are not getting a whole number. Okay? Earlier on, when we did the expansion for 3 minus 4 root 3, I'm also not able to get whole numbers. Okay? So, for example, increase this. Okay. If I have 1 plus 3 root 3 squared, and I want to use my identity of a plus b bracket squared, so that will give us our a squared plus 2ab plus b squared. And that results in 1 squared plus 2 times 1 times 3 root 3 plus 3 root 3 squared. Okay? And that gives us 1 plus 2 times 3, 6. 3 root 3 bracket square, that will give us 9 times 3. So we have 28 plus 6 root 3. Okay? Even if I have, let's say, 1 minus 3 root 3 squared, using similar identity, I also do not arrive at a whole number. Okay? So I'm not able to so-called get rid of the square root symbol. Okay, if I were to do the entire thing squaring it, okay, or over here squaring it as well, I'm able to get whole numbers, okay, when I achieve a product like that. Okay, because I apply my a plus b bracket, sorry, a plus b times a minus b to get a square minus b square. Because we know that, okay, when we were to square a square root, okay, I'm able to get a whole number. And this is an important concept, okay, because that ties in with our understanding of conjugate surds. Okay, so what conjugate surds are? They are so-called opposite expressions, whereby one is actually in the form a plus b, the other one is a minus b. So we're making use of this pair later on when we want to rationalize a surd. Right? Okay, even if you have expressions such that both of them, okay, both terms have surds inside it, I can still do my a square minus b square to achieve a square minus b square, such that I have 2 square root 7 square minus away square root 3 square. And this will give us 4 times 7 minus 3. So we get 5. Okay? So with this observation, we see that conjugate surds, okay, will refer to a pair that is in this kind of form. Okay, one of which is a plus, the other one is a minus. denominator. Okay, what do we mean by rationalizing the denominator? It will mean that in the denominator itself, we do not want the square root sign to be inside it. Okay, but we want to ensure that it is still equivalent, that they are still equal. I cannot randomly bring the square root sign up, okay, into the top of the fraction. Okay, I must make sure that I do intentional steps, okay, they are actually accurate and correct. equals to 2 over square root 7 times square root 7 over square root 7. Will we agree that they are equal? They are equal, right? Because essentially what I've just done, although I've introduced the multiplication of root 7 over root 7, what is this value over here actually? 1. Okay? So I'm multiplying by 1. It doesn't change the value of my question. Okay? Why is it that I chose square root 7 over square root 7 and not something else? That's because I know that in my multiplication of fraction, I take numerator times numerator, divide by denominator times denominator. Okay, so I'm trying to see it in this manner. Okay, and root 7 times root 7, that will give us 7. So I have successfully shifted the root 7 over into the numerator. Okay, in other words, I'm trying to get rid of the square root sign in the denominator itself. So in rationalizing the denominator, our aim is to remove the surd from the denominator. Yes, okay, but it cannot anyhow remove lah. Okay. Right. Now let's consider part B. Okay. Part B is slightly different because in our denominator, we now have an expression of 5 minus 2 root 5. Okay, how am I going to decide what to multiply? Okay, so what we did over here in part A was that I intentionally multiplied by something that will actually kind of remove the surd in our denominator over here, because we know that root 7 times root 7 will give us a whole number 7. Okay, and this entire thing over here is equal to 1. Okay, and it doesn't change the value of the question. So what we want to do in part B is that we also want to maintain the value of the question such that they can be equal. So I want to multiply by something that is equal to 1. Okay, so how am I going to decide what is it to multiply? Okay, that's where I rely on the idea of conjugate surds. Okay, so we recognize that a pair must be 1 plus the other one minus. So in this case, this is minus. I want to multiply by its plus version. Okay, but I cannot just multiply by 1 over 5 plus root 5 because this is a value itself. Okay, you cannot multiply by some random number because otherwise they won't be equal. So my numerator must also be the same. Okay, so now we have numerator times numerator over denominator times denominator. And in our denominator, I can apply my a squared minus b squared, which is 5 squared minus away 2 root 5 squared. Okay, numerator we have 50 plus 20 root 5. Okay. So the thing about knowing our conjugate pair helps us to get rid of the root sign in the denominator, because in this case with 2 root 5 bracket squared, that will give me 4 times 5. Because 2 squared is 4, root 5 squared is 5. Okay? Right? And then we can achieve 25 minus 20, that will give us 5. Okay? But is this the most divided by 5 plus 20 root 5 divided by 5. Okay, so 15 divided by 5 is 10. 20 divided by 5 is 4. So the simplest answer will be 10 plus 4 root 5. Questions? Okay, I do one last one. Then we can really call it a day for this term. Okay, part C we have this. Okay, sorry. I gave one answer. This was the question. Okay. So with this, observing the denominator, because we're trying to address the denominator, we will multiply by 2 root 5 minus 2 root 2 over 2 root 5 minus 2 root 2. Because this is the conjugate to 2 root 5 plus 2 root 2. Okay? So, in our denominator, I can apply a square minus b squared. Such that we get 2 root 5 squared minus 2 root 2 squared. In the numerator, we will have to do our rainbow method, our expansion individually. So root 5 times 2 root 5, that will give us 2 times 5. Okay. Root 5 times negative 2 root 2. Followed by 3 root 2, or rather negative 3 root 2 times 2 root 5. Okay, and then lastly, negative 3 root 2 with negative 2 root 2. Squeeze in here. And then a plus 3 root 2 with 2 root 2. Okay. And then in the denominator, 2 root 5 squared, that will give us 4 times 5. 2 root 2 squared will give us 4 times 2. Okay. Now, all this complicated multiplication over here, how do we simplify them? Okay. The square root can multiply by the square root. So, we will take 5 times 2 to get the number to be found inside the root. So, this will give us 2 root 10. Okay. Followed by 3 times 2, that will give us 6. Root 2 times root 5, that will give us 10. 3 times 2, again it will be a 6. Root 2 times root 2 is actually just 2. Okay. Denominator, you can press your calculator for it. 4 times 5 is 20, 20 minus 8, that will be 12. Okay. Then we can continue to simplify this. 10 plus 6 times 2, that will give us 6 plus 12, 22. Minus 2 root 10 minus 6 root 10, that will give us a negative 8 to 10. Such that we get 22 minus away 8 to 10 over 12. Still can simplify because we have common factors. I can divide by 2. So this will be the most simplified answer. Okay. Go back home, go and try it inside your notebook. Okay, you must go and try it. Sorry that I delay a little.